All right, if you're on Zoom, please type something into chat and all that jazz. The roll sheet is going around for the in-person folk. Yes. When I'm within 6 feet of anyone else.
I think they said it takes a little while to kick in anyways.
I think it's supposed to be like 2 weeks after the second dose.
How you feeling?
Significantly better than Friday.
Friday was bad. I can't lie.
Oh yeah, because you got your second dose on Thursday too,
Yeah,
or
Thursday morning,
Yeah.
around midnight, I'm like, nope, that class ain't happening Friday.
well, wasn't happening for me either, apparently.
I still haven't slept. I was like, okay, yeah.
Yeah, no, I couldn't do anything but sleep and shiver. Like,
I was just shaking. Seriously, I was like, I couldn't go to sleep because I was just like, and my dog was looking at me like, what?
no, I had like my sheet, a blanket. I have like this Saints throw, and then I stole my wife's electric blanket and had that guy cranked up. Yeah, I was just sitting there shivering, and I woke up in the morning and was trying to get ready to go to work and all this kind of stuff. I felt terrible, but I felt bad for having to miss after the first shot, and I was like, I don't want to do that again. And I was so tired and fatigued that I was dizzy, and I was talking to my wife, and she was like, you can't drive, like you're going to kill yourself or somebody else. You can't drive. You have to talk to Dr. Turner and figure this out. And so by about, I think 8:00 a.m., I was back in bed asleep and woke up at 4:30 p.m. So I took a solid 8-hour nap after sleeping the entire night through, and then was asleep again by 9 p.m.
Yeah, I was in bed the next night at 9 p.m. Woke up, it was like noon the next day. It was weird.
Yeah. So
And then it was fine.
yeah, by Saturday morning, I was like, all right, let's go to the grocery store. Let's get stuff done. So, excuse me. All right, so that is still not what it's supposed to be. So, there is a distinct possibility that we will have to spend about 10-15 minutes on Wednesday covering new material that will be on the exam Wednesday night. I can tell you that the material that we will be covering on Wednesday can be answered in 10 seconds because it's just a simple theory question. So you're not going to be missing out on anything because you don't have time to practice it. All right. So today we're going to talk about Cascode differential pairs once I get all my junk organized in a way that makes sense to me. And then we are going to talk about common mode signals because we've spent this entire time talking about differential signals because our common mode has always been rejected. And we're going to mess that up by including a resistance for our current source. So, Cascode differential pairs. All right, so let's start with BJT. Where we'll have something that looks like this. What?
I think it was a homework problem.
Yeah, I mean, the analysis portion of this is going to take us next to no time. It's probably going to take me longer to draw the circuit than to analyze it. And you guys probably have noticed there's at least 2 homework problems that you have no idea how to do. We'll knock those out today. so let's call this guy transistor Q1, Q2, Q3, Q4, Q5, Q6, Q7, bless you, Q8. Here's VCC. We're going to call this guy VB7, this guy VB5, this guy VB3. Here's V out 1. Here is V out 2. So since this guy is perfectly symmetric, we can split it up into its equivalent half circuits, which is going to look something like this, where I'm doing the small signal, turning off all of my power supplies and all that kind of jazz. Let me call this guy VID over 2. This is going to be ground. This is going to be ground. This is going to be ground. Here is V out, or actually VOD over 2. Let's see, Q7, Q5, Q3, and Q1. And so it should be fairly easy to see that our half circuit looks identical to a Cascode amplifier, right? Our input is applied at transistor, the base of Q1, the output is taken at the node between Q3 and Q5 here. So let's see, that would be the collectors of Q3 and Q5 respectively. And so we can find the differential gain by analyzing this circuit as if it were a Cascode amplifier. So I'm going to call everything looking up R not P, everything looking down R not N. And from this, our differential gain, AV comma D, is negative GM1 R naught N in parallel with R naught P, where R naught N is 1 plus GM3 R naught 1 in parallel with R pi 3, close bracket, R naught 3 plus R naught 1 in parallel with R pi 3, close bracket, and I'll try to squeeze it in here. R naught P is going to be effectively the same thing, but with the right subscripts for the other transistors. So that's 1 plus GM5 R naught 7 in parallel with R pi 5, R naught 5 plus R naught 7 in parallel with R pi 5. When GM3 times R naught 1 in parallel with R pi 3 is much greater than 1, and GM5 times R naught 7 in parallel with R pi 5 is much greater than 1. This reduces to negative GM1, GM3, R naught 1 in parallel with R pi 3, in parallel with GM5, R naught 7 in parallel R pi 5. Yes.
Are we supposed to? Without going to small signal, it's like I just need to review cascoding. Is that like?
Yeah, I mean, that's literally where those resistances came from, is for a cascode.
And then you also got rid of R naught 1, R pi 3, R naught 7, R pi 5.
Right. So when this guy is much greater than 1, it dominates. So if this guy is much larger than 1, then it's significantly larger than these guys in parallel as well, because it's being scaled by a factor, right? Yeah. So GM3, trying to make sure. Okay. So sorry, I actually did make a small mistake here. So thank you for catching things and making me think about it real quick. So this is supposed to be GM3 and whatever I had there. Let's see. So it should be GM3, but there should also be the R naught 3 here. So this guy multiplied by this guy multiplied by the parallel combination. And same thing on the other side. So that would be GM5, R naught 5. So thank you for pointing that out, because it did seem odd without that factor in there. All right, so that is the BJT. The MOSFET is effectively the exact same thing. Just for the sake of argument, we'll go ahead and draw it out and all that kind of jazz. Excuse me. So for our MOSFET, it's going to look like this. ISS. Here's VN2, VN1. Let's call this guy M1, M2, M3, M4, M5, M6, M7, and M8. Which would make this guy VG7, VG5, VG3. Here is Vout1. Here is Vout2. Effectively the exact same thing we had before, but with MOSFETs instead of BJTs. So our half circuit should be effectively the same thing. Sorry, my hand is cramping up. VOD over 2, VID over 2. So it still looks like a Cascode amplifier where this is M1, M3, M5, and M7. And from this, again, our differential gain is negative GM1 times R naught N in parallel with R naught P, which for our MOSFETs comes out to be negative GM1, 1 plus GM3, R naught 3 times R naught 1 plus R naught 3 in parallel with 1 plus GM5 R naught 5 times R naught 7 plus R naught 5. Excuse me. Under certain conditions, we can kind of neglect a few things. So let me define what those are so that we can do a simplification. So when GM3 multiplied by R naught 1 multiplied by R naught 3 is much greater than R naught 1 or R naught 3 individually. And when GM5, R naught 5, R naught 7, and R naught 7, this guy reduces to negative GM1 times GM3, R naught 1, R naught 3 in parallel with GM5, R naught 5, R naught 7. Now, obviously, these are all based on that simplification. The short circuit transconductance, GM1 multiplied by the output resistance. So in your homework problems or problems in the textbook and all that kind of jazz, you might see things where, say, this cascoded PMOS current source is replaced by a resistor or an ideal current source or something like that, and you simply replace R naught P with that equivalent resistance. So this is, excuse me, more classical way of doing the circuit, and then we can do subtle variations as are necessary. So any questions before we move along from how these guys behave from a differential mode standpoint? All right, feel like we've been beating this to death pretty good. So common mode will be a nice change of topic. All right. So thus far, all of our BJT and MOSFET based differential pair amplifiers have used an ideal current source to provide the tail current, right? And that ideal current source, by definition, has an infinite resistance or an infinite impedance. And that is what has caused all of our common mode signals to be completely rejected. If we include some finite tail resistance, we are going to find that we no longer have total common mode rejection. Instead, we are going to see some common mode gain, and we'll talk about that momentarily. And when we get into our common mode gain analysis, that's really not going to be terribly important, meaning it's not going to have too much of a problem associated with it, because we're still taking a differential output, meaning we're going to be amplifying both of our input signals by that same common mode gain and then taking the difference, so it's going to cancel each other out. However, if we have mismatches in either the resistors that we are biasing these guys with or the sizing of the transistors, particularly in the case of MOSFETs, we're going to see that a change in a common mode signal at the input can cause a change in the differential output, which can be considerably bad. So that's what we're going to spend the next several minutes talking about. So let's consider the following circuit. And I'm going to do all these guys with MOSFETs because it'll make the math a little easier and therefore a little quicker. So what I am attempting to depict here is that we are going to apply some signal Vn common mode to the inputs of both transistor M1 and transistor M2 simultaneously. So the exact same signal, that's why it's common mode, is applied to both inputs. And in addition to that, we now have, excuse me, a tail current ISS, and we're going to place in parallel with this tail current ISS a resistance RSS. So effectively, just to be really clear here, everything I've outlined in this crappily and hastily drawn orange box represents the Norton equivalent circuit of any practical current source we might use to bias this thing, right? So it's representative of transistors or whatever it is that we happen to use to provide this tail current. All right, so I'm going to clearly define VGS1 and clearly define VGS2 as well. All right, so let's talk our way through this to some extent, all right? So let's say that our common mode voltage, V in common mode, is changed by a small amount, so that we're looking at this thing from a small signal perspective. What is the relationship between ID1 and ID2 going to be? So if we increase the common mode voltage or decrease the common mode voltage for that fact, ID1 should change and ID2 should change, but they should change by the exact same amount because the symmetry requires that ID1 be exactly equal to ID2, right? What's interesting though, is that the change in the common mode voltage also causes a change in the voltage at node X, right? Because if we change that common mode voltage, we are changing VGS1 and VGS2. Our currents are going to change, but they're going to change by the same amount so that they're still equal. But we'll see that that node at voltage X is now a floating potential effectively that can move up and down. It's no longer pinned to be exactly at 0. And the reason for that is because that small change in current is going to flow into this resistor RSS. Small signal model, this guy looks like an open circuit, so all the change that we observe is going to flow through that resistor RSS. And so since current is flowing through the resistor RSS, there is a voltage drop associated across the resistor RSS, which happens to be the voltage at node X. So we're going to see that it's going to shift up and down accordingly due to small variations in our input common mode signal. So since our large signal currents ID1 and ID2 are equal, what can we say about the relationship between Vout1 and Vout2? They should also be equal. Absolutely right. So since they are at the exact same potential, does it hurt anything if I connect those two nodes with a short circuit? Not at all, right? Because they have to be at the exact same potential. So if I short out Vout1 and Vout2, what I'm going to have is something that looks like this. Go away. So this is going to look like RD over 2. V in common mode. Here's V out, transistor M1, transistor M2. This is ISS, and I still have my resistance RSS. Transistor M1 and M2 are identical. That's really just a single transistor with twice the area, right? So if we treated it as a single transistor with twice the area, we're applying some input signal here at the gate. We're taking the output here at the drain. What kind of amplifier is this? Yeah, common source. But it's being degenerated by this resistance RSS, right? Small signal, we no longer see this guy ISS, so we have a simple common source amplifier being degenerated by a resistance RSS. So our common mode voltage gain for this guy is just the gain of a common emitter amplifier that's being degenerated by that resistance RSS. So I can say that AVCM, common mode voltage gain, is going to be the change in the output voltage divided by the change in the input voltage, which is going to be negative RSS plus 1 over twice GM RD over 2. And the reason why I have twice GM here is because it's two transistors in parallel. So we get twice the transconductance because it's twice as big. And if I multiply through by 2GM in both the numerator and the denominator, this becomes negative GM RD divided by 1 plus twice GM RSS. For MOSFETs, and we can assume that the BJT is going to work in effectively the exact same way. So this would be negative RC over 2 times REE plus 1 over 2 GM, or negative GM RC over 1 plus 2 GM REE, or a BJT circuit. All right, so just as a kind of a quick aside, because it's going to be useful momentarily when we break this by no longer having perfect symmetry, based on this voltage gain, where we have neglected channel length modulation and the early effect respectively, what is my short circuit transconductance of these guys? If I know my voltage gain, AV, whatever it is, I know that that has to equal negative capital GM times R out, right? So just as a quick aside here, because we're going to use it momentarily, what is my short circuit transconductance? All right, let's look at this amplifier real quick here. What is R out? RD over 2. All right, so let's try for my short circuit transconductance again. It's negative 1 over this guy, right? Because we just factor out the RD over 2. Yeah. Or similarly, we could factor out the RC over 2, and it's negative 1 over REE plus 1 over 2 GM. Okay. So just wanted to make that clear because we are going to use it. All right, so one thing that should be fairly obvious here, we have a common mode gain, meaning we are seeing a change in our single-ended outputs, Vout1 and Vout2, which are both just represented by this quantity Vout, due to a change in our common mode input signal. When we take that differential output, that common mode gain goes away, right? We don't actually see any change in our differential output whatsoever. So we're effectively just raising and lowering the DC operating point of our output signal and then subtracting out the DC portion when we take that differential output. But if we were to change the value, so we have right now a resistor RD and another resistor RD. What if one of those resistors was slightly mismatched? That's what we're going to look at next. Okay. Sorry, what was that? It actually doesn't turn out to be that terrifyingly bad. Like, how could you, let's talk about how could you ever precisely match two resistors? You can't. There's no way that they're going to be exactly the same. Even within the same fabrication run, even located directly next to each other on a chip, there's going to be subtle variations in either the size or the properties in some way or another. So you're never going to have two exactly perfectly matched resistors, nor are you going to have two exactly perfectly matched transistors. We just do the best we can. So with that in mind, let's take a look at this guy. So I'm going to call this guy right here RD1, which has a value of RD. This is our current ID1. Here's our output voltage V1. Here's our output voltage V2. RD2 and this guy is going to have a value of RD plus some variation delta RD. Here is ID2. Here is VDD. And we're tying our inputs together and applying some common mode voltage VNCM again. Let's call this guy transistor M1, this guy transistor M2, and as per usual, we will have some tail current ISS, but now our tail current has some resistance RSS, all right? So, since our transistors are perfectly matched, if VCM increases by some small amount, let's call it delta VNCM, all right, then our drain currents ID1 and ID2 have to increase by the exact same amount, okay? And that amount is given by our transconductance that we talked about a moment ago, okay? So if VNCM increases by delta VNCM, ID1 and ID2 increase by a factor of GM divided by 1 plus 2GM RSS delta VN. Our short circuit transconductance using the second expression. All right. So since RD1 and RD2 are not equal, Vout1 and Vout2 are not equal. So they don't change by the same amount. And so we could say that the change in Vout1 is going to be negative delta Vn common mode multiplied by Gm over 1 plus 2 GM RSS. So that's our change in current multiplied by our resistance RD. Delta Vout2 is negative delta Vn common mode, excuse me, Gm over 1 plus twice GM RSS. And this guy is going to be multiplied by RD plus delta RD. And when I take the difference of these two changes in output signals, I get the change in my differential voltage signal, right? So from this, delta VOD, the change in my differential output, is negative delta Vn common mode Gm over 1 plus 2 GM RSS times delta RD. So I can see that a change in my input common mode signal generates a change in my output differential signal, okay? So we are going to quantify this by what's called the common mode to differential mode conversion gain, AV CM-DM, and it is going to be defined as the absolute value of the change in VOD divided by the change in VN common mode. And in this case, that is simply GM delta RD divided by 1 plus 2 GM RSS. And the textbook says that we can simplify this as effectively delta RD over 2 RSS, but I tell you explicitly your homework does not use that simplification. So web work potentially won't like it, just letting you know right off the jump. So I would use this guy right here. This one is derived for MOSFETs. For BJTs, because they behave similarly, we'll have GM delta RD over 1 plus 2 GM REE, which is approximately delta RD over 2 REE. You're right. Thank you. For BJTs, where we have to assume that IC is equal to IE to make this work. Otherwise, there would be a factor of alpha thrown in there too, which the textbook ignores. All right, so now we come to another question. How bad is this? All right, and the answer is it depends, okay? So if we have a small differential gain, this can be potentially pretty bad because we have a common mode gain, which is doing what? So we have GM times some change in resistance, relatively small, right? So if the two resistors were just wildly mismatched, that would be a bad design to begin with. We're really looking at things where the mismatch is on a relatively small scale here, right? So we have GM times some small number over 1 plus twice GM times the output resistance of our current source, which is typically pretty large, which means our common mode to differential mode conversion is usually a pretty small number. So if our differential gain is larger than that, this really isn't that big of a deal. And we quantify that by a property called the common mode rejection ratio, okay? So the common mode rejection ratio, CMRR, this is something that if you got a data sheet for an op amp or something like that, it would explicitly be told to you, is going to be 20 log the absolute value of AVD, so that's the differential voltage gain, divided by AVCMDM, the common mode to differential mode conversion gain. Typically speaking, most op amps have a CMRR of around 80 decibels, okay? So that means that typically speaking, the open loop differential gain is about 10,000 times larger than the common mode to differential mode conversion gain. So it's usually pretty dang good, but if you design your op amp poorly, this can become a rather large issue. And this is where the textbook stops on problems with common mode signals. But I'm going to take it one step further because I'm a glutton for punishment. We're going to look at what happens if our transistors don't match as well. All right. So if we have a transistor mismatch, let's say that we have this circuit. So we have some resistance RD, Here's V out 1. Here's ID 1. Here's our second transistor. Tying our inputs together yet again. Common mode input signal. REE. No, mixing things up here. RSS, apologize. Here is VDD, and we are going to be working under the assumption, because this looks perfectly symmetrical, so there shouldn't be an issue, that W over L1 is not equal to W over L2. What implication does this have? And let's say that we're going to ignore common mode, channel length modulation, as we have been, because it just makes the math terrifyingly difficult on these guys when they're asymmetrical. So ignoring the effects of channel length modulation, if the size of our transistors aren't perfectly matched, what transistor quantity is also not perfectly matched? Transconductance, right? Because transconductance is square root of 2 mu n C ox W over L times ID, right? So assuming the transistors are made in the same process, mu n should be the same for both. C ox should be the same for both, although it doesn't necessarily have to be, because there are processes. If you have a 2 polysilicon process, you can actually have 2 different oxide capacitances, because you could use those 2 different poly layers as your gate if you wanted to do that. Probably way more in depth than you guys need to know is the technology available. But anyway, so the transconductances, GM1 will not be equal to GM2 for whatever reason, likely just due to simple mismatch in transistor sizing, okay? So since M1 and M2 are not identical, ID1 and ID2 can't be identical either, right? So if we had a small change in our common mode voltage, we're looking at this guy as a small signal problem again, we're going to see that the voltage drop over this resistor RSS, or the voltage at node X, is dependent on the sum of the changing currents that are flowing into that guy, right? So I can say that my voltage Vx is RSS times GM1 times delta Vn common mode minus Vx plus GM2 delta Vn common mode minus Vx. All right, so all I'm saying here is the current ID, the change in the current ID1 is the transconductance multiplied by VGS1 plus the transconductance of transistor 2 multiplied by VGS2. right? That's my drain current 1, my drain current 2, add them together, and they flow through this resistor, giving me this voltage Vx. And so I can rearrange this guy, or actually, simplifying things a little bit, this gives me GM1 plus GM2 times delta VNCM minus Vx times RSS. And from this, my voltage at node X is GM1 plus GM2 times RSS divided by 1 plus GM1 plus GM2 times RSS, all multiplied by delta Vn common mode. So now that I know how Vx is changing, that lets me figure out how my output signals are changing as well, okay? So delta V out 1 is going to be negative GM1 delta Vn common mode minus Vx times RD. So that's how much a small shift in my common mode level causes a change in the output voltage. So I just have GM1 times VGS1 gives me the current, multiplied by the resistance gives me the change in the voltage, just to be clear where, excuse me, this stuff is coming from. And if I substitute in my definition for Vx, this becomes RSS, that's my denominator. Up here, I have negative GM1 RD delta Vn common mode. My change in Vout2 is going to be negative GM2 times VGS, so Vn common mode minus Vx RD, which looks like negative GM2 RD divided by 1 plus GM1 plus GM2 times RSS times delta Vn common mode. Excuse me. And finally, my change in my differential output is then negative GM1 minus GM2 times RD divided by 1 plus GM1 plus GM2 times RSS, all multiplied by delta Vn common mode, giving me a common mode differential mode voltage gain of GM1 minus GM2 RD divided by 1 plus GM1 plus GM2 RSS. So a small mismatch in the transconductances also generates an output differential voltage as well. So something to take care of. And if we wanted to figure out how much this affects things, we could have used our exact same definition for common mode rejection ratio as before, just using this particular common mode to differential mode conversion gain to quantify it. All right, so I think that's enough out of me for today. 'Cause my hand is cramping up like crazy. Anybody have any questions about the homework or anything like that, since we do have 15 minutes or so? A few people have asked questions about problem 3.
Yeah, I see that.
Okay, so let's look at problem 3 real quick.
I'd like to have the right formula.
All right, so doing this partially from memory, so tell me if I'm doing something wildly wrong. We have a PNP BJT with some resistance R1 that is connected in this fashion. And here is B out 1. And then we have VN1 tail current IEE, and then the other side is identical, so I'm not going to bother drawing, right? All right, so the instructions in the homework problem are actually pretty legit, telling you to effectively just find R naught P and then use that to make your life easier. So I'm going to be clear about what we're doing. We're looking in through that output terminal, and we're trying to find this output resistance R naught P. So I'm ignoring everything below that output voltage node, and I'm going to draw my short circuit model. So I have, let's see, here's my base for transistor 3. Because it's a BJT, I have R pi 3, which means this is V pi 3. This is my emitter. Here is GM3, sorry, V pi 3, not R pi 3. Here is R naught 3. This is my collector terminal for transistor 3. So my emitter, just to be clear, emitter, base, collector. My emitter is at AC ground. I have a resistor R1 between my base and my collector. And this node right here that I've just drawn a little terminal on is my output node. And you are told to use a 1-volt test source. I'm not even going to go into that big of a detail. I'm just going to use a generic test source, VX. And this is my test current that's leaving that source, IX. And so just using good old Kirchhoff's current law, I can say that IX is VX divided by R naught 3 plus GM3. And I need to express V pi 3 in terms of VX. So I know that my potential difference from this node to ground is Vx. So I can use voltage division and say that V pi 3 is just R pi 3 over R1 plus R pi 3 times Vx. And lastly, I have Vx divided by R1 plus R pi 3, right? What's up?
So nothing wrong with that. We're slightly confused on why we're allowed to just
So this is the Thevenin equivalent. We're in a small signal, right? So this only works because we're looking at this small signal. We have a two-terminal network where one terminal is here and the other terminal is ground. So from the perspective of the rest of the circuit, we can isolate this guy and get the Thevenin equivalent resistance and treat it as if it were a resistor. Right? That's the beauty of Thevenin equivalent circuits. So that's why we can disconnect this part and say it looks like this, because to the entire rest of the circuit it does. So yeah. So I know that it's not intuitively obvious because you don't get, or you're not required to use Thevenin and Norton equivalent circuits all the time. And even when we're doing them, sometimes we don't say, hey, this is what we're doing, but that's literally all that this is. So I have Ix on one side, Vx on the other side. So if I have Ix over Vx, that's going to look like 1 over R03 plus 1 over R1 plus R pi 3 plus GM R pi 3 over R1 plus R pi 3. If I flip that guy over, it then just looks like 3 resistances in parallel with each other. And so we can see that R naught P, which is Vx over Ix, is R naught 3 in parallel with R1 plus R pi 3 in parallel with 1 plus R1 over R pi 3 times 1 over GM3. And then we can just throw that in as if it were the resistor RC and treat this like any old simple differential pair circuit.
I don't see what I got wrong.
Okay, well.
And then I looked up online, like another way of doing it, and it worked because it replaced something with the beta IC to get rid of, like, to use IB, start adding current together, and I was like, okay, well, I got the right number for doing that, but I don't see what I did wrong. Maybe I calculated.
Yeah, R pi is going to be what, beta IC over VT? Something like, I mean, there's.
Yeah, because it was using, because we know IC, so it got IB. To get, I guess that means we know V pi.
Right.
And that was just plugging stuff in.
Nathan, what's up?
Whenever we draw a small signal for CNC, that's like, maybe this is my confusion from what I learned last quarter. I feel like it shouldn't be the correct up.
How does that change anything?
It doesn't have a retarding fault.
Yeah, no, I understand exactly what you're saying. E should be up here, but the positive polarity should be down here, right? The change is nothing.
And what,
Because if we flip this guy about its axis, so let's. You are suggesting, just so that we're all on the same page. No, it's. We'd have GM3, V pi 3 in parallel with R naught 3. This is now our emitter. This is our collector. So this is our output node. Here we have R pi. This is V pi 3. No, that should be between the base and the emitter, sorry. All right, so there is R pi 3. Here is V pi 3. This is our base. This is R1. That's ground, right? What's different? Absolutely nothing. Like I understand intuitively that in a BJT transistor, the emitter is at a higher potential than the base and the collector. And so that's why some people choose to draw it this way. And for a large signal analysis, 100% of the time, that's what I'm going to do. But the beauty of BJTs and MOSFETs is that their small signal models are identical, regardless of whether you use NMOS or PMOS or NPN or PNP or however you want to do it. So like, I understand why it's confusing because it's not the way you're taught, but they are literally identical. In small signal, yes. So no, there's nothing wrong with being like, why is this asshole doing it this way? I got no problem with that whatsoever. But I believe I've drawn this correctly, and it is literally this flipped over. Anything else? We got 5 or 6 minutes left. Let's see. Anybody seeing anything in the chat? Nope, just people telling me that they're here.
Knowing what to turn things into, like what kind of resistance.
Fair enough, yeah. And that's going to be a lot of the exam as well, being able to quickly identify, okay, so that one is diode connected, so it looks like R naught in parallel with 1 over GM. Yeah.
Because I'm like, oh no, a diode, that's this, the current source.
Yeah. So there is a very specific reason that I went over all that at the very beginning before we started talking about cascodes and all that kind of stuff. Yes, I'm sure it was, and I would highly expect to see some of that show up on your equation sheets as well. Yeah. Yeah, no, for the equations, yeah, I usually have to go back through and like R naught. I think that one's easy for me because it's 1 over lambda ID or VT or yeah, VA over IC. So that one's easy, but remembering the equation for R pi trips me up pretty much every time. So I have to have that one written down and look at it. So, and then transconductance, that one makes sense to me because by definition, it's the transconductance is how well a transistor converts a voltage into a current. So it's got to be current divided by voltage. So it's IC over VT, or for MOSFET, it's a big equation. Yeah. Square root of twice mu n Cox W over L ID. Yeah. So yeah, write that crap down on your equation sheet. You're going to use the hell out of it.
I'm still a little stuck on the whole like figuring out the resistances and impedances of like the cascading BJTs and MOSFETs. Like I haven't reviewed it yet, obviously. And is that something that will click when I go to the textbook, or is there like a trick that I should be?
I don't understand your question. I mean, it just is.
And then in one line, you had all of it, and it was just I just didn't know what you were going. I didn't know what was going on in your head.
Sure. Okay.
Like,
All right. So let's come up here then. That's fair. So you guys are talking about this specifically. All right. So I look at my half circuit. Let's just do the MOSFET one. Okay. I'm looking at my half circuit. I see that my input is applied at my gate. My output is taken at the drain of this other transistor. So this guy right here is for sure a cascode amplifier, and it is being loaded by a cascode current source. Okay. Using my short circuit transconductance definition of gain, meaning it is negative capital GM times R out, I know that for any cascode amplifier, the short circuit transconductance is equal to the transconductance of whatever transistor I'm applying my input signal at. We mathematically derived all that crap. So that's how I go from capital GM to lowercase gm in one fell swoop, okay? R naught N, since I know that this is a cascoded NMOS transistor, if I'm trying to find the output resistance of this guy, what do? To find the output resistance, I short out the input and I look in through here. So the output resistance of this guy is going to be the exact same thing as the output resistance of a NMOS cascode current source, because both of these guys are at the same potential. And so then I just look in my notes and say, all right, so the output resistance of a cascode current source is this guy right here. The hardest part for me is in the textbook and in the notes and all that kind of stuff, the way that they derived the output resistance for the cascode current source was transistor M1 was here and M2 was down here, so I have to remember to switch my subscripts accordingly. That's the only part, in my opinion, that requires thought. Everything else is just identifying it and say, I know how that behaves, so I'm going to just substitute that in.
So that is just kind of like.
Yeah, and I mean, memorization, in as much as you get an equation sheet, it's just identifying that's a cascode. So it works this way. Yeah.
We have not quite that messy on homework, where I was like working it out and I'm like, this looks familiar. And I was like,
yeah.
I wasted a lot of time trying to figure out mathematically how it, and I was like, oh, I have to.
Yeah, I mean, so I've tried to do the heavy lifting for you and get you to a point where you can say, this is how it works. And so you can go from here to here, because for the most part, that's all you need to know. Like legitimately, even in practice, they're not going to be like in granular detail, you need to rederive everything. No, there are books and resources for a reason. Yeah, I noticed trying to help you with your homework a couple of weeks ago, I was like, you're doing all of this stuff and we can walk you through it, or you can just say, you know what, that's this. So let's just, call a pig a pig and use that equation.
Have a formula sheet's going to be like this, and then arrow, this is the resistance. This arrow, this is the resistance.
Yeah. I mean, that's what I would have done if I had to make an equation sheet for any of this thing. I would draw a picture, and I would, if it's an amplifier, I would write down the equation for the gain, the output resistance, and the input. That's something that we haven't talked about. What are the output resistance any of these amplifiers are going to be? A differential amplifier. So if we know the output resistance of this, it's 2 of it because they're in parallel. Or is it?
Are you talking about the entire?
Yeah, of the whole thing. It's yeah, because they're in parallel. Yeah. So for the whole thing, right? If we had this guy right here, this whole thing, and we wanted to know what the output resistance was, we can treat it as if it's these 2 half circuits in parallel with each other. That's it. So if you know the output resistance of the half circuit, you know the output resistance of the whole circuit.
For the Cascode,
Yeah.
there's like the simplification you can do. Do you have to like make sure that simplification works every time? Like the GMs are bigger than the.
I personally don't like using the simplifications literally ever. I know on your homework it can be hard to say, well, should I do it or should I not do it? I will say that the person that authored the questions 9 times out of 10 uses the simplified form. And unfortunately, the simplified form deviates just enough from the unsimplified form to make WebWork reject your answer. For the exam, where it is a handwritten calculation, I'm good either way. If you're going to use the simplification, I would justify it. Meaning just do a quick calculation and say, because this is less than this thing, I get to do this. Or because this is much greater than 1, I get to do this. I mean, you have an equation sheet, so you can write down both or whatever. I'm not going to. I don't have the time or patience to go through and nitpick, oh, well, he made this, but he shouldn't have, or blah, blah, blah. No, it's just going to be what it's going to be. All right, see you guys on Wednesday, where we're going to talk about loading this guy with a current mirror, and then that's it. And review.
Okay.
Yeah.